Okay. All right. So, well, last time we have studied this Hamiltonian constraint, and especially we are able to quantize the first term in Hamiltonian constraint, which is what we call Euclidean term. And however, we know that there's a second term. So this is something we are going to study, and this is what we call Lorentz term. Okay, and maybe I write again the quantization of the Euclidean term. Well, C hat 0 V. So V is the replacement for this X. X is a space-time point. It's a spatial point, and V is the vertex of the lattice lattice. And this is given by I square theta 1, and this is a prefactor, and you sum over S1, S2, S3 equals plus minus 1, and also I1, I2, I3 equals 1, 2, 3, and S1, S2, 3, 2, 3. Okay, and we have a trace. This is the trace of the SU2 Lie algebra, or trace of 2x2 matrices. And alpha is the minimal loop around a plaquette. Vertex 3. And then there's this HHV term. Okay, so this is the quantization of the Euclidean term with Hamiltonian constraint. Okay, so now this lecture we are going to just finish the entire quantization of the Hamiltonian constraint. So we just need to compute the quantization of the Lorentz term, and you can see that the Lorentz term has a identical term similar to Euclidean term, and this is and this term will be just this HHV. Okay, so you can replace this term by using Poisson bracket of holonomy and volume. Okay, just like the just like this term. Yeah, we have treated this term as just a holonomy and the Poisson bracket between holonomy and volume. Okay. All right. So now we are going to just rewrite this Lorentz term in terms of trace of SU2 Lie algebra, like what we did for Euclidean term. Okay, so now let's talk about Lorentz term. Okay, and so firstly, CLX can be written as minus kappa theta square plus 1. Well, this beta is Babel image parameter. I think most of you should remember. JMN. Well, it can be written. Now you replace this minus 1 by 2, and you replace, you put a trace. The trace is between two commutators. Q commutator. Okay, and here you see this K is KAI. It's just a matrix version of K. Okay. And KAI is just extrinsic curvature, right? KAI is extrinsic curvature. So here it is something not so explicit. It is that this K, actually this C, this Hamiltonian constraint is a functional of holonomy, or it's functional of S-Tuck connection and the density triad. It should be a functional of A and E, right? But this K, so I put a K here, so it means that this K, AI is actually 1 over beta and AI minus gamma AI. No? So because A is H-Tuck connection is gamma plus beta K. So therefore K is A minus gamma divided by beta. So actually this K should be written in this more explicitly in terms of this. And this gamma is a function, is dependent on E, and A is the H-Tuck connection. So this Hamiltonian constraint is just a function of A and E. So this K is just viewed as intermediate variable. Right. All right. So you can see that what we have done is just to replace this epsilon KK factor to be a commutator between K and K, and this epsilon EE to be the commutator between E and E. Okay. So these commutators are all respect to the Lie algebra. So they are commutators of 2 by 2 matrices, and the trace is also respect to SU2 Lie algebra or 2 by 2 matrices. Okay. And so here we are going to use the same formula, Tiemann's trick, to rewrite this term. Okay, rewrite this factor. Okay, and so similar to the Euclidean term, what we are quantizing